Welcome back, folks, to our final unit where we are going to be discussing acids and bases. These are some unique chemical compounds that result in some very unique chemical properties. So we're just going to dive on in and start talking about what makes acids acids and what makes bases bases and how they interact in solution. So the learning targets for today, hopefully by the end of this video, you'll be able to explain some basic concepts of acids and bases. You should be able to differentiate between weak and strong acids and bases, and also explain how acids and bases react with each other. We have a ton of vocab terms for this video, including binary acid, oxyacid, Arrhenius acid, Arrhenius base, strong acid, weak acid, Bronsted-Lowry acid, Bronsted-Lowry base, monoprotic acid, diprotic acid, triprotic acid, Lewis acid, Lewis base, conjugate acid, conjugate base, amphoteric, neutralization, and salt. All right, I know you guys got all that down, so let's move on. So what makes acids acids? Well, acids are chemicals that are sour tasting. Acids are found in a variety of different things that you see on a daily basis. You look at lemons. Lemons contain citric acid. Ants contain something that's called formic acid. The root form actually refers to ant. Milk is actually acidic. It has lactic acid in it. You probably, like I said, heard these terms before. Lactic acid is also what builds up in your muscles and causes that nasty pain you get when you're running and exercising. Acids react with metals to release hydrogen gas. We may look at a demonstration of that later on in class. Acids react with bases to produce salt and water. Acids can also conduct electricity because they are electrolytes. They do dissociate in water. There are two major types of acids that we're going to focus on. One is known as a binary acid, and you know that the root bi means two. So binary acids just contain two elements, hydrogen and an electronegative element. Another type of acid we're going to look at is known as an oxyacid. The root oxy refers to oxygen, so oxyacids include hydrogen, oxygen, and some form of a nonmetal. You'll get to know some of these acids a little bit later on. Now, properties of bases are a little bit different. Bases usually taste bitter and feel very slippery. They do react with acids to produce salt and water, and as they are also electrolytes, can conduct electrical current. So some common bases would include things like sodium hydroxide, that's something that's found in drain cleaner. Magnesium hydroxide in milk of magnesia for when you got that really nasty tummy ache. Sodium bicarbonate, baking soda, ammonia, things that are used to clean. So bases are very common as well. We'll take a look at this a little bit detailed later on. So what are some types? How do I identify acids and bases? Well, the first types of acids that we're going to look at are Arrhenius acids and bases. And Arrhenius acids increase the H plus ions in solution. So these are things that typically have a hydrogen before them. So for example, HCl, hydrochloric acid, is a acid. When you put it in water, just like you see in number 1, HCl breaks down into H plus and Cl minus ions. It increases the H plus ions, which increases the acidity of it. Now, Arrhenius bases are kind of different. They increase OH ions in solution. So what we're looking at primarily is H ions versus OH ions. When you add an acid or an Arrhenius acid, you increase the H plus ions because the H comes from the HCl. Arrhenius bases increase OH ions in solution. So for example, sodium hydroxide, NaOH, you put that into solution, it will break down into Na plus and OH minus. Based on how many H's you have per OH's, that's how you determine how acidic or how basic something is. If there are more H's than OH's, then your solution is acidic. If there are more OH's than H's, then your solution is basic. Now, there are some differences between strong acids and weak acids, and same thing with strong bases and weak bases. Strong acids completely dissociate in solution, meaning if I take the acid and I put it into solution, all of it's going to convert into H and its ions. And there are 7 strong acids. There's HI, H2SO4, HCl, HBr, HClO3, HClO4, and HNO3. So these acids completely dissociate in solution, so you get all of the H plus ions. Weak acids, however, only partially dissociate in solution, meaning that only some of it is going to break down into its individual ions. The rest of it is going to stay together. So that's pretty significant because strong acids increase the H plus concentration significantly, whereas weak acids only increase it slightly. There's the same concept with strong and weak bases as well. Strong bases are just simply anything that's group 1 and group 2 plus and hydroxide ion. So very, very similar concepts here, but make sure you're able to differentiate and understand the differences between strong acids and weak acids. And same thing with strong bases and weak bases. If it's strong, it completely dissociates. All the particles are going to break down into the individual ions. If it's weak, only part of it's going to break down. And that significantly impacts how acidic or basic a solution can be. Another type of acid we will look at is the Bronsted-Lowry acid-base model. In this particular instance, Bronsted-Lowry acid is a proton donor. So in this instance, it is going to donate a proton. It's very, very similar to the Arrhenius acid model because hydrogen is a proton in this aspect. So if you look at the reaction here, the HCl donates that proton to water. So in this instance, HCl acts as the acid, the water acts as a base, because Bronsted-Lowry bases are proton acceptors. So it all depends on which one accepts a proton and which one loses a proton. So for example, in that first one, HCl is an acid. Your water then is a base. If you take a look, the HCl donates a proton to water, thus making it H3O plus and Cl minus. So in this instance, HCl is your acid. If you look underneath, NH3 becomes NH4 plus. It accepts a proton from water. So as a result, if it accepts that proton from water, we create an OH ion, which is representative of a base. So in this instance, the NH3 is the base and the H2O is the acid, because H2O donates that proton to NH3. So it really all focuses on which one accepts the proton and which one donates the proton. When we talk about acids, we talk about different types of acids, and there are quite a few different types, but in this instance, we're talking about how many hydrogens it can provide. So if there's only one hydrogen there, that is known as a monoprotic acid, meaning that it only donates one hydrogen. It can only donate one. So for example, HCl is monoprotic. Diprotic acids can donate 2. So H2SO4, there are 2 hydrogen ions that it can donate. There's even triprotic acids, which can donate 3 protons. H3PO4, phosphoric acid, is an example of a triprotic acid. These are all nice because they use those wonderful, wonderful roots that we all know and love, mono, di, and tri. Lewis is a name that you've probably heard of before when we've talked about Lewis dot structures. Lewis acids accept an electron pair to form a covalent bond, and Lewis bases donate an electron pair to form a covalent bond. So in this instance, the oxygen here is the Lewis base because it's donating its electrons to form a covalent bond, whereas the Lewis acid here, SO3, is accepting that pair of electrons to form the covalent bond. So, like I said, we won't talk a lot of detail about this one. The main ones I want to focus on are the first two that we previously discussed, the Arrhenius acid model and the Bronsted-Lowry acid-base model. Now, when we talk about conjugate acids and bases, we have to look at what we have at the beginning and look at what we have after. So a conjugate base is the product after an acid has donated a proton, and the conjugate acid is the product after the base has accepted the proton. So when we look at the example here, H2SO4 in water, H2SO, based on the reaction, H2SO4 donates a proton to water. So as a result, H2SO4 is my acid, and water is my base. Now, water accepts a proton. Because my water has accepted the proton, it's become H3O plus and therefore is known as my conjugate acid. So our base becomes our conjugate acid. Our acid becomes our conjugate base because it has donated a proton. The example here, H2SO4 becomes HSO4 minus because one of the protons has been donated to that water to create H3O plus, also known as hydronium ion. So keep that in mind that they kind of pair up together, a conjugate acid-base pair. The acid from the reactant side becomes the conjugate base on the product side, and the base on the reactant side becomes the conjugate acid on the product side. So some substances are known as amphoteric. The root amph means both, like the word amphibian, because they have a part of their life cycle where they live on land as well as water. An amphoteric substance can react as either an acid or a base. The classic example of this is water. Water is H2O. Depending on what you put in it, it can accept a hydrogen ion, thus becoming acidic, or it can donate one, thus becoming basic. So it really just depends on what you are adding into solution. Which reminds me, let's make water the word of the video. Water is the word of the video. Now, when mixing acids and bases, the reaction of hydrogen and hydroxide to form water causes neutralization, resulting in salt and water as your products. So when you mix an acid and a base, you get salt and water. It's just the nature of it. We'll do a couple chemical reactions with that a little bit later on, but you mix an acid and a base, they react with one another, they produce salt compound and water. Long story short, well, there's a lot that's going on here, and you probably should have watched the whole video. Lots of really good stuff in here, so unfortunately you're not going to get away with looking at this time. Sorry, guys. But hopefully you did expand a little bit on your learning targets for today. Hopefully you had a good time watching this video. I know it's a lot of information. We're going to spend quite a bit of time reviewing this in class before we move forward. This is JLand Bio signing out. Have a great day, guys, and we will talk to you later. Bye-bye.